Thank you for coming to this week's colloquium. It is my pleasure to invite Nicolas, who is a colleague from my time in Centrum. So Nicolas has his PhD awarded in the Marseille, and then he had a postdoctoral position at some period in Warsaw with Eva Walkers. Then he took his own Sonatina grant to Toulouse at UNV, and he's currently based in the University of Florence. He's going to tell us about cosmic ray in simulations of all type of galaxies. So Nicolas, welcome. I will take off the lights.
Hi, everyone. Thank you, Mariana, for the introduction and for the invitation to give this colloquium. So yes, today I would like to talk a bit about winds. In this presentation, I'm going to talk about winds or outflows. They have a very similar meaning. What I mean by this is large amounts of gas that are traveling at a galactic scale. This is an illustration of the galaxy seen from the edge, where you have a lot of outflows of wind gas that is leaving the galactic disk into the haze. So I'm looking at galactic outflows, and I would like to look a bit at the impact of cosmic rays on the production and on the composition of outflows. So let me introduce a bit. Yes.
Something about scales. If you would project Milky Way on the previous slide, so how it would look like? Because that's an image which does not resemble a galaxy as I basically know it from popular science. This is as far as I'm competent in this subject.
Mm-hmm.
It's neither oblate or doesn't have characteristic shape of what is believed to be like a spiral galaxy. So,
So
explain this image, please.
Sure. So this is just an artistic illustration, but this is a galactic disk seen from the edge. So basically, the white part you have here is just you have your spiral galaxy, which resembles the disk, and if you look at it from the edge, and you look at the gas that is outflowing from the disk out of the disk into the halo.
So in other words, it's much bigger than the galaxy itself.
The outflows,
Yeah.
in this case, yes.
Yeah.
So you have, of course, we'll come back to this, but you have different types of outflows. So you can have very powerful outflows that can reach very big distance, that can even completely leave the galaxy.
But isn't this misleading because column density of this outflow will be orders of magnitude lower than the column density of actual cold gas molecular constants? So this is just illustration, but
This is only an
over
illustration.
exaggeration just for destructive
Yeah.
purpose.
But it depends on which wavelengths you're looking with. Yeah, of course, you will always have the disk.
Direction of this outflow, shall I understand it immediately, or why it's perpendicular to the
Yeah.
this?
So it is a gas that is accelerated vertically out of the disk. Yeah. So I will come back to this. I will explain a bit details about this. So yeah, so I'm interested in winds that are launched by cosmic rays. So I will explain a bit how this works. So well, just to introduce a bit cosmic rays, so I'm interested in galactic cosmic rays. So usually on Earth, when we talk about cosmic rays, we talk about mostly about solar cosmic rays, so cosmic rays accelerated and produced by the sun, typically in solar flares. This is not the type of cosmic rays I'm interested in because the energy of the solar cosmic rays is way too small to have an impact at the galactic scale. So there are different types of cosmic rays with different energies, and the type of cosmic rays I'm interested in have very high energy of giga-electron volt, and they are produced. So cosmic rays are those high energy charged particles, mostly protons and electrons, which are traveling at relativistic speeds, mostly along the magnetic field lines through the galaxy, and they are thought to be mostly produced and accelerated in supernova remnants. So this is a process called Fermi acceleration. So the way it works is when you have a star exploding, so you have a supernova explosion, this creates a very powerful shock wave, and this shock wave will propagate outwards. And then you have those particles like protons or electrons or heavier ions that will be trapped around the shock wave due to the very strong and turbulent magnetic field you will have around the shock wave. Those particles are called, are said to surf the shock wave because they're basically traveling and bouncing back and forth between the upstream and the downstream region of the shock wave as the shock wave is propagating outwards. And every time they travel through the shock wave, they actually gain some energy. And at some point, the energy is so high that they're able to escape completely the supernova vicinity. And at this point, the velocity is close at such a high velocity that they can travel through the galaxy and even out of the galaxy, and they can very easily escape the disk and move vertically into the galactic halo. So I'll just show a very simple illustration here. So very basic scheme. So here you have your galactic disk seen from the edge again, and the little stars here represent a bunch of supernova explosions you will have in your disk, which is particularly concentrated in the center of the galaxy usually. I will come back to this later. But the way it works is as the supernova explode, they release cosmic rays. The cosmic ray will travel within the disk, but they will also escape the disk and travel vertically. As they do this, they will settle a pressure gradient. So you'll have more cosmic rays within the disk and out of the disk. But you will see this cosmic ray pressure gradient pointing towards the disk. I also show here the result of one simulation made by Michał Hanesz in 2013. So this is representing the cosmic ray energy density. Yes.
Something doesn't add up for me. Maybe,
Yes.
well, I don't know. Maybe I misunderstood you, but as far as I'm concerned, what you were explaining, the mechanism of the production of this cosmic ray in supernova remnants, the protons and electrons start as subrelativistic velocities, and they just accelerated. But the escape velocity of an object like that is orders of magnitude lower. You don't need to be relativistic to free stream away from the supernova remnants. So how come they are trapped for so long, then only can escape when you get relativistic?
So it's mostly because of the very high magnetic
So
turbulence.
this was the very important part I
Yes.
missed. So this is, but
Yes.
do we know there's such a strong magnetic turbulence in the remnants, which are quite large?
Yes, around the shock wave. Yes, it creates
Okay.
very strong magnetic turbulence, and those protons.
Right,
are
there's only small region when you can produce them effectively, I understand.
Yes,
The
it's around the
okay.
shock wave.
That was what I was missing, okay, thanks.
Yeah, so here this is the result of one simulation of a spiral galaxy. So you have the spiral galaxies from the top edge, face on the top, and you even see a bit of the spirals in the cosmic rays. And if you look at the edge on view of the galaxy, you really see those cosmic rays propagating vertically out of the disk, and you can effectively see here this gradient of energy density of the cosmic rays. So this pressure gradient is very important for us because cosmic rays actually interact with the gas in the galaxy. Mostly through scattering and collisions, they actually transfer energy and momentum to the surrounding gas. And this is actually a very efficient mechanism to accelerate gas just from the cosmic ray pressure. And because of this cosmic ray pressure gradient, you can actually accelerate gas out of the disk and create very powerful outflows and winds in the vertical direction. This is something I'm illustrating here. Here I'm just putting this result of one of my simulations where I'm computing the acceleration only, the gas acceleration only made from this cosmic ray pressure gradient. And you can see it's especially strong very close to the disk. So you have your disk here seen from the edge, again in dark, and you see those.
And it's not isotopic because around pressure in the disk forbids to propagate the propagation along the disk. That's why the only degrees of freedom are left are perpendicular. That's
for the gas, you mean? Yes, yeah, indeed. So
around
for
pressure.
yeah, exactly. For the gas, it's very difficult to propagate within the disk because of the high density. The halo has a much lower density, so the gas can very easily accelerate.
Sorry for interruption, but some things
No,
I
that's
want
no
to
problem.
understand.
All right, so those
No,
galaxies.
if there is so large gas density, and only, I don't know how many supernova explode per unit time, astrophysical period of time, it seems implausible that basically this cosmic rays can move as effectively as sketched here, this large amount of gas accelerated to the height of just too few cosmic rays, basically.
Well, so it depends indeed on the supernova explosion rate. So a very active galaxy that forms a lot of new stars and young stars will actually create a lot of supernova explosions, especially close to the center of the galaxy, which is usually where the highest gas density is and where you form a lot of new stars. And as a lot of supernova explode, it kind of builds up over time because the cosmic rays will go in all directions. Some of them will leave the disk, but a lot of them will also stay in the vicinity of the disk. So the interesting thing about cosmic rays is that their pressure builds up over time. So you will not form those cosmic ray driven outflows initially from the start, but as you have more and more cosmic rays, this pressure gradient builds up over time, and at some point it starts to really have a significant impact on the gas movement. So those galactic outflows are a very hot topic at the moment, and we're trying to understand a bit more how galactic outflows work and what's their structure. So you have to know that the idea of implementing cosmic rays in simulations of galactic outflows is a relatively recent one. So for a long time, most simulations and models were assuming that outflows were creating solely from thermal energy. So basically when a supernova explodes, so I talked about the cosmic rays, but it also injects a lot of thermal energy, heats up a lot the gas around it. And this alone is sufficient to create outflows. If you heat a lot of gas, especially in the center of the galaxy, this gas will also struggle to propagate on a radial scale because of the high density, but it will be able to leave the disk and propagate into the halo. However, from this classical picture of outflows, there's a number of features in observations that are a bit difficult to explain. So in particular, the presence of multi-phase gas, so you will have gas with different temperatures, different metallicities, which are not so easy to explain if you only infer outflows driven by thermal energy. We also find very large-scale outflows that are even leaving the galactic disk into the intergalactic medium, of gas leaving the galaxy into the intergalactic medium. There's also the observation in our own galaxy, the Milky Way, of the so-called Fermi bubbles, which are very large gamma and X-ray structures. I will come back to this later, but this is what is shown here, that above the center of our galaxy, we have those kind of bubbles that extend very far out of the disk, seen in gamma ray and X-ray. This is also pretty difficult to explain. I will come back to this a bit later. And basically, overall, the presence of outflows when you don't have that many supernova explosions, that's much of star formation in the galaxy. So we're trying to understand a bit more the outflows and the mechanism driving outflows, and the cosmic rays is a relatively recent topic in this. Most models actually studying outflows do not include any cosmic rays, but it's a very promising field to understand a bit more observations and outflows in general. So to study this, I'm going to use a code called Pianic. Pianic is, of course, was developed in Torun. So I guess most people in the room know what Pianic means, but if there's any non-Polish speaker, well, Torun is a city mostly famous for two things. So first, it's the birthplace of Nicolas Copernicus, but most importantly, it's the capital of gingerbread in Poland. Yeah. And as most of the people in this room probably know, but for any non-Polish speaker, Pianic means gingerbread in Polish. So this is how the name was chosen, of course. It's a code that was developed by Michał Hanacz and his team, and it's a grid magneto-hydrodynamical code that allows to make galaxy simulation or simulations of the interstellar medium, including cosmic rays. So the cosmic rays are treated as a diffusive gas. So typically in a simulation of a galaxy, initially we do not include any cosmic rays. The cosmic rays are added and implemented over time as supernova strike, so as supernova explodes. The way it works is every time a star explodes, we inject, so the amount of energy injected by a supernova is typically around 10 to the 51 Earth. And we inject 90% of this energy in the form of heating, so just thermal energy, and the remaining 10% will be in the form of cosmic ray.
Do we have any motivation for this ratio?
This 10%? This is actually something that's not very well constrained.
Free parameter for your model.
Kind of. I mean, it will not be 100%. It will not be 1%. People usually use something between 5 and 20% from the models. It's somewhere between there. It's very difficult.
Because if you get it too small, there's no effect, and if you get it too large, there's some catastrophic consequences, I guess.
Kind of.
It's like a general bracketing from be compatible for observations, something like that.
So, I mean, also from the Fermi acceleration process, you can kind of estimate how much cosmic rays are going to be accelerated, but it is also sometimes fitted indeed to the observations. Let's say between 5 and 20% is good. good constraint. But
Okay.
I use 10% kind of in the middle, but this can be changed a lot a bit. It will have an impact on the outflow production, not massively, unless you really put a very low or very high value, but it will have. Okay, so the cosmic rays are treated as a diffusive gas, and in the code they propagate through the advection and diffusion transport equation that I show here. So this just shows the evolution of the cosmic ray energy density, the ECR. And you have here the cosmic ray pressure. And the most important parameter in this equation is the diffusion coefficient, kappa, which I put here. So the diffusion coefficient is anisotropic because the cosmic ray diffuse preferentially alongside the magnetic field line and will still diffuse but much less perpendicular to the magnetic field. So this is what I show here, and the value I take for in the direction parallel to the magnetic field is 9 × 10⁻28 centimeters squared per second. This parameter, unfortunately, is still poorly constrained as well. People use something between 10 to the 7 and 10 to the 27, sorry, 10 to the 29.
That depends on the morphology, the disk, whatever, right? Somehow.
Not so much. I mean, no, I mean,
it's a phonological parameter.
I mean, it will be impacted by the morphology of the galaxy, but the coefficient of diffusion should be relatively independent to the type of galaxy. But this is a bit poorly constrained, so we're also trying to fit this to two observations in terms of outflows. Of course, if you use a very small diffusion coefficient, most of your cosmic rays will stay within the disk. If you use a very high, they will all leave very quickly. This can, of course, have an impact on the results. And in the perpendicular direction to the magnetic field, we use 1/100th of this value. On top of this, Fizyki also allows to have n-body particles, which will model the stars and the stellar disk, also the dark matter. And on top of this, we will have a gaseous disk. So I will go a bit more into details about how I built my model. So I'm taking a Milky Way type galaxy, so more or less the mass and the morphology of the Milky Way. So we start with a dark matter halo made of 500,000 n-body particles, stellar disk, also 500,000 n-body particles. And then the gaseous disk, which is projected on the grid, is built in hydrostatic equilibrium with the other components. So here with this grid, we have a resolution of a bit less than 200 parsecs. I'm going to show here a video showing the evolution of the stellar disk. So those are the stars, projected density, and you see here face on at the top, edge on at the bottom. You see the development of spirals and a very strong galactic bar in the center here in red. So this is very typical for a spiral galaxy. Yeah, I mean, it looks very simple. We evolved the galaxy for 1.7 giga-year. The stellar particles are also interesting and important for supernova. So the way we implement our supernova, so our stellar explosions, is so we initially have some star particles that are already in the disk. And then in the high density regions, we form new stars. So we form new stellar particles. This is called sync particles because those are the particles that are here put on the grid, and as they travel around the center of the galaxy, they will accrete gas over time until they reach critical mass, at which they release. Basically, we consider the ones they reach a critical mass, they explode. So they release a supernova feedback. So as I described earlier, 90% of the energy will be injected in the form of heating, so thermal energy, and 10% will be this cosmic ray energy. On top of this, we also include stellar winds and radiation pressure, which is basically we only implement it as a form of momentum injection before we inject this.
This is the single phase, right? Hydrodynamics. So you have only one
in the gas
equation of phase.
Yes. Yeah. So we don't have.
Gas is always cold, can form stars. You don't.
You need a dense. So there's a density threshold and a temperature threshold. So dense cold gas.
Yeah, but when you say that you take 90% of thermal energy, this is just a kinetic feedback, right? You don't actually heat the gas. You change the equation of.
No, you do heat the gas. So there's you change the internal energy of the gas.
And then this gas is not available for star formation, right? In your,
If it's too hot, yeah, of course, yeah.
okay.
So you just locally heat the gas at each supernova explosion, and then you see what happens. So you will, of course, lose some gas this way for the star formation.
Right, so you need to keep somehow a trace of the cold and hot phases of the gas.
Yeah. So I mean, we have thermal gas in the simulation. So
Okay.
yeah. So we have different temperatures.
No,
Yes.
I mean, what in the Galactic Hydrodynamical simulation, so.
Yeah.
This is very essential.
Yeah,
Just, I wanted to understand, okay.
No problem.
you
Yeah.
have
So
a
we have
complex-
some, but I mean, but we have only one phases. We don't have molecular gas. So we only.
How do you cool the gas? It's just some table for the element by element cooling, or?
So we have a cooling curve. Yeah.
Okay.
All right.
Thank you.
Sure. So I talked a lot about stellar particles. This is the last time I talked about stellar particles because the component I'm interested in is the gas. First, I'm looking at the outflows. So let's look a bit at the gas component. So I said that we build this gaseous disk on top of the stellar and halo components. On top of this gaseous disk, we also implement gas accretion from the intergalactic medium. So this has been shown to be a very essential, important component for building galaxies, is that you will have gas that will be accreted from outside the galaxy, from the filaments, typically, or from the intergalactic medium. And so this represents this stream feeding from galaxies. It will also allow to enhance and sustain my star formation because you bring new gas that will allow to form new stars. It will also bring angular momentum to the disk. I'll come back to this in a minute. And it lasts for about 1 gigayear. I will show here the gas density evolution. So you have it face on at the top and edge on, and you see the stream of gas arriving from the center for 1 gigayear. So at the end, the gas component forms also some nice spirals and a bar that follows more or less the stellar component. Now I'm going to play this video again. I would like you to focus on the bottom panel, so the edge on view. And we'll see the creation of outflows. So you see all this gas that is leaving the disk. So the disk is this very bright line. You can see all this gas that is leaving this. This is the outflows that I'm interested in. So this is what I'm studying.
May I ask you,
Yes.
the external flow is the source of the angular momentum?
So it is, yeah.
Only.
No, I mean, the gas already has rotation and angular momentum at the beginning. So the initial disk already has circular velocities.
So you put galaxy by hand there, right? Just from initial conditions.
The initial conditions is a kind of uniform gaseous disk with on circular orbits. And on top of this, we had this stream of gas. All right. And so this, I just showed you one simulation, but we actually have a sample of 5 simulations here. Which is basically the only difference between those 5 simulations is the velocity of this stream of gas accreted. So from left to right, I'm increasing the velocity of the gas accreted from the stream. And this basically changes the amount of angular momentum I'm bringing to the disk. I will illustrate this right now. So I'm showing 3 of those simulations. So the extreme left, extreme right, and then the middle one. And you see the velocity of the stream is different, and the morphology of the galaxy in the end will be quite different as well. So you can really see here, you have a very small and compact gaseous disk. As you go to the right, you form a much more extended disk, which makes sense because you're just adding more momentum, angular momentum to your disk.
Magnetic fields do not contribute to the gas dynamics here, right? We just use
A little
locality
bit,
for the-
not much. The magnetic field mostly contributes to the star formation. In terms of gas dynamics, very little. Well, it interacts with the cosmic ray, so indirectly. But again, I will play those videos again and I'll ask you to look at the bottom panels this time. So the vertical motions of the disk. If you look at the outflow production between the 2, they are pretty similar at the beginning, but as time goes by, you can start seeing more outflows. I don't know if you can see it really well here on the left and on the right. On the right, the outflows seem to stay closer to the disk. If you cannot see here, it's fine. You can also just measure it. So this is the outflow rate. So this is just the amount of gas that is leaving the disk as a function of time. And here I'm showing it for those 5 simulations, this panel of simulations. So from blue to red, you're just increasing the amount of angular momentum of the disk because you have a higher velocity of the of the stream accreted by this. And what we see is the outflow rate is indeed scaling pretty strongly with angular momentum. So you have a much lower outflow rate. You create less outflows for the cases with high angular momentum. Actually, this is something we can correlate. So we have an anti-correlation between the total outflowing mass and the angular momentum of the disk.
So what was the mass contributed in the stream compared to the mass already present in the disk?
Yes, I think it's about 10%, if I remember correctly. Something like this, a bit less. Yeah, kind of, yeah. You can compare it.
What happens if the external source of momentum is against the initial momentum?
Yeah, that's interesting. So I'm not presenting it here, but yeah, indeed, we tried because the stream is accreted within the disk plane, and in the case I showed, it's indeed in the same rotation direction as the disk. If I do the opposite, then indeed the stream is counterbalancing the rotation of the disk, and then you form an even smaller disk actually. And if I didn't put it on this panel, but you would get an even higher outflowing rate in this case, because the resulting angular momentum of your galaxy would be even lower than my blue curve here, because you have almost zero angular momentum of very low. All right, on this anti-correlation between outflowing mass and angular momentum, I'm just going to add very quickly another set of simulation, which is a set of simulation where I did not include cosmic rays. So we can still do the same analysis without cosmic rays. So it's exactly the same simulations with the stream accretion, everything, but no cosmic rays. So as I introduced, you can still form outflows without cosmic rays, just from the thermal energy, thermal pressure. But as you see, they don't lie on the same correlation line. But you still have a correlation with the angular momentum. I will come back to the simulations in a few minutes. I just want to explain why we have this trend of angular momentum and with outflowing mass. To understand this, we can look at the star formation rate as a function of time, which is shown here for this 5 simulations with cosmic rays still. So the star formation rate is simply the amount of new stars formed as a function of time. And you can see that the star formation rate is much higher for the low angular momentum disks than for the high angular momentum disks. So it scales pretty well with the outflows overall. So the explanation behind those high amount of outflows for low angular momentum disk is simply that, as you've seen, if you have a low angular momentum disk, you form a very small and compact galaxy. If it's for the same amount of mass, gas mass, so basically the densities in your galaxy will be much higher. And if you have higher densities, then you form more new stars. The star formation scales very strongly with the density.
But I need to stop you here for a second. Yeah. You make a big leap in a faith, in the sense that scales that are needed for resolving molecular clouds for star formation and this particular densities are way smaller than whatever you can resolve here. So it seems you submit physics.
Yes.
Explain that if you have a galactic scale, higher density, you form more stars. Yes. Which I'm not saying is unreasonable. I'm saying it's not just a consequence of direct physics, but something that you put down.
Some physics for sure. So I mean, our model for star formation, our criteria are based solely on density and temperature, and it follows basically more or less. I forget the name. It's a law that exactly. Yeah, I mean, yeah. that follows. It's basically the star formation rate is more or less density to the power 1.5, more or less. So that if you have stronger densities, you have more star formation. So it's of course subgrid physics. We are very far from resolving the actual. We actually cannot even resolve a single supernova explosion. So we can.
I'm just mentioning because we know there are starburst spiral galaxies we observe in quite in the universe that have relatively low central densities, but actually very high activity star forming.
Exactly.
So I'm not saying that they are representative for everything we do, but there's a contrary example. Can we also?
I mean, the star formation, the star formation can depend on many factors, of course. But usually, if you have very high densities and very cold, dense gas, you expect to have a lot of star formation, unless there's something disrupting or taking the gas away.
So if I can,
could we just move on? That's okay from 7 to 9.
We can come back to the side.
Yes.
All right, so you have those very small compact disks with very high densities, and if you have higher gas density, you have higher star formation rate. And if you have a lot of new stars formed, then those young stars will quickly after explode in supernova explosions, and you have more supernova explosions. And if you have more supernova explosions, then you have more outflows. So I would just like to really highlight this, because I will come back to this later, this very important dynamics here, where you have high gas density that will create a lot of new stars that will, in return, create a lot of supernova explosions, and therefore more outflows. Okay, so now that I explained a bit the link between angular momentum and outflows, I would like to come back to those simulations I introduced earlier, which do not have cosmic rays. So here the two top panels are the simulation with half cosmic rays, and the two bottom panels are the exact 5 simulations, but without cosmic rays. So the only difference between the two is that every time a supernova explodes, instead of injecting 90% of thermal energy and 10% of cosmic ray energy like we were doing, we just inject all the energy in the form of thermal energy. Let's look a bit how it looks. So this is a case with cosmic rays and without cosmic rays. So if you look at the face-on view, the evolution is fairly similar. But if you look in the edge-on view, you see that you create much more outflows on the left in the case with cosmic rays and without cosmic rays. So this is, of course, something we can measure. And this is, again, the outflow rate, so the amount of mass, of gas mass leaving the disk as a function of time. In blue with cosmic rays, in red without cosmic rays. And we can see that the case with cosmic rays indeed creates much more outflows. So why is this? Well, this is simply due to this mechanism I explained at the beginning, where you have this pressure gradient of cosmic rays that will, through interaction with the gas, push more gas out of the disk. So you have both the thermal pressure that is, as I said, a low enough to push some gas out of the disk, like in the case without cosmic rays, and on top of this, you add this cosmic ray pressure gradient to accelerate gas even further out. If we look at the star formation rate, the amount of star formed as a function of time, a bit surprisingly here, you see that the case with cosmic rays actually has a lower star formation rate. So this is pretty much the opposite of what I said earlier, that if you have a higher star formation rate, you expect more outflows. But here again, you have this additional mechanism of cosmic ray pushing gas out of the disk. And the fact that the star formation rate is lower in the case with cosmic rays is actually an effect of the outflows. So what you see is at the beginning, the star formation rate is very similar between the two cases. And as the cosmic ray pressure gradient builds up, this starts accelerating more and more gas out of the disk. You start creating more and more outflows in the case with cosmic rays. And this outflows is removing gas from the disk. So basically, you're pushing gas out of the disk, and this gas will not be available anymore for star formation, because of course stars are formed from this cold, dense gas. And therefore, you will have a lower star formation rate in this case. So what we see here is what I already highlighted a bit before, is you really have basically a feedback loop between the star formation rate and the outflow. So if you have high star formation rate, you will create a very high outflows, very strong outflows, and this will remove gas from the disk, and therefore you actually lower your star formation rate. And this is kind of why you see those kind of cycles of strong star formation bursts followed by a lower star formation burst, because lower star formation rate simply because as you create a lot of hot gas and a lot of winds, then you remove effectively gas for the star formation. All right, now I've talked a lot about outflows in terms of masses and outflows and densities, but let's look a bit at the phase of this outflow. So I'm going to look here at the temperatures maps in the case with and without cosmic rays. So if you look at the bottom panel, you can see the outflow production in terms of temperature is very different between those two cases. You can see that with cosmic rays, the outflows are much cooler than without cosmic rays. This is something we can also quantify. Here I'm showing the temperature distribution in the disk at the top panel and in the outflows at the bottom panel with cosmic rays and without cosmic rays. The different colors simply show different stages of the galaxy evolution, so different times. And if I look at the case with cosmic rays in the outflows, what we can see immediately is we have a binodal distribution with a warm phase around 20,000 Kelvin and a hot phase around 1 billion Kelvin. However, if I look at it without cosmic rays, you can see, well, there's a very small bump here around 20,000 Kelvin, where it's completely negligible. And most of the hot phase is actually, most of the outflow, sorry, are in hot phase. So pretty hot, very hot gas, actually between 10 to the 6 and 10 to the 7 Kelvin. So if I summarize a bit, in the presence of cosmic rays, you create more outflows that go to higher altitude due to this cosmic ray pressure gradient. You also create some hot gas in the outflows due to this thermal energy injected in the supernova, but you also accelerate cooler gas out of the disk, and this creates this warm phase that I just described. If you remove cosmic rays from the picture, then you see you create much less outflows, and the outflows will stay close to the disk, which basically creates a mechanism called as a galactic fountains, where you push gas out of the disk where it doesn't go high enough to really leave the galaxy, and it will fall back eventually, and that's why we call it a fountain. It will be recycled into the galaxy. And you can see that you only find hot gas in the outflows. There's no warm phase or cooler gas. Let's try to understand a bit why, in the presence of cosmic rays, we have those two very separate phases of the warm phase and the hot phase. Let's visualize a bit spatially how they look. So this is the case with cosmic rays. I'm just showing those two phases that I described before, so the warm phase and the hot phase of the outflows, how they are distributed spatially. So I'm putting the cold and warm gas together here, and you can immediately see that most of the warm gas actually staying pretty close to this. So you go up to maybe 15, 20 kiloparsec maximum. Well, if you look at the hot outflows, they actually go much further out to 40 kiloparsec or even higher in altitude. To try to understand this, let's look at another observable, which is the angular momentum of the gas. So here I'm checking, similar to the temperature, I'm checking the specific angular momentum of the gas in the disk and in the outflows. Again, the colors represent different stages of evolution of the galaxy. And here in the outflows, we again see this kind of bimodal distribution with a low angular momentum phase close to 0 and a high angular momentum phase close to 3,000 kiloparsec kilometers per second.
So you only plot JZ, but there might be high angular momentum in the other direction.
Well, I mean, most of the angular momentum will be LZ, right? Because the disk is rotating, and therefore the outflow center also be there. Of course, you could also look at the other angular momentum, but this is the component I'm interested in, because it will, I mean, I will show how relevant it is in a second. So if I try to plot a bit spatially again those two phases, so the low angular momentum and high angular momentum phase, well, the difference between the two phases is not as striking as for the temperatures, but you do see that the low angular momentum phase, well, of course, you'll find most of the low angular momentum gas in the center of the galaxy, and it tends to go to higher altitudes than the high angular momentum phase, with more gas at the periphery of the galaxy. So this is something we can measure, of course, as well. So here I'm showing the mean temperature and mean angular momentum of the outflowing gas as a function of altitude. And what it shows is basically as you go away from the disk, you start finding more and more hot outflows and at low angular momentum. We can also quickly visualize those four phases put together. So it's the same as I've already shown before. So cold, warm phase, hot gas, low angular momentum, high angular momentum. And if we do this, we see some similarities between those phases. It seems like the cold warm phase and the high angular momentum phase have a lot of overlap. We find those outflows that tend to stay closer to the disk, while the hot and low angular momentum phases also seem to be fairly similar, with outflows going pretty far out of the disk. There's something we can see here. So this is a phase diagram of those two parameters I introduced. So the specific angular momentum of the gas as a function of its temperature in the top panel here. So of course you'll have gas that spans a bit the entire phase diagram, but we find some very strong concentrations of gas where I circled here. So in the red circle shows this hot gas with low angular momentum, and the blue circle is the high angular momentum gas with the lower temperature, so warm phase. This is just showing the cylindrical radius, so the distance to the center. Here, as expected, the high angular momentum will be found at higher radii than the low angular momentum phase. So yeah, we have those two. If I simplify the picture a lot, we'll have roughly two phases in our outflows. This warm gas with high angular momentum that is typically at the periphery of the galaxy, and that will the outflows will stay closer to the disk, and we have this very hot phase with low angular momentum is closer to the center, and we go to much higher altitudes. This is important because this means that this hot gas with low angular momentum will be, some of it at least, permanently removed from the center because it goes to such high altitude, 40 kiloparsec and above, that it will not be reaccreted by the galaxy, or at least not within a reasonable time. While the warm gas with high angular momentum will typically stay closer to the disk and be reaccreted by the disk and recycled into fountain flows. So to try to explain a bit the presence of those two separate phases, I'm going to look within the disk at the thermal and cosmic ray pressure here as a function of the cylindrical radius. So this is within the disk because this is where the outflows start from. If I look at the thermal pressure in red, I see that the thermal pressure is rather high, up to 5 kiloparsec, and then it drops very brutally, as you see, and after 5 kiloparsec radius, it becomes pretty negligible. This is simply because the hot outflow phase, the hot gas, so the thermal pressure, is very dependent on the density of supernova explosion. The hot gas doesn't propagate much radially within the disk, so it will be mostly concentrated where most of the supernova explosion are, which is in the center. So you will have a very high star formation region in the center, so a lot of supernova explosions, and you will heat your gas a lot. But the moment you go to the periphery of the galaxy, you have much more scattered supernova and much more sparse, and your thermal pressure suddenly drops a lot. So this explains why in the center you have such hot outflows, right? Because you heat up the gas a lot from the supernova explosions, and this is the gas you will find in the outflows. This also explains why the gas is accelerated to such high altitudes, because I'm showing here the vertical velocity of the gas in the outflows as a function of their temperature. And you can see that the highest velocities of the gas as they leave the disk, vertical velocity is reached for the highest temperatures. So in the center, you have those very hot outflows that leave at very high velocity, and this will allow them to reach very high altitudes above the disk.
What is the escape velocity of your dark matter halo? Maybe visiting the galaxy together.
So the dark matter?
And gas, I guess it's around 400 meters per second, something like that.
The gas is typically around, I mean, the circular velocities are around 1 to 200 kilometers per second. The dark matter.
Because you make this argument that the altitude is too high to get recycled, but your simulations are vacuum boundary conditions, so you don't track the gas actually, you just remove it. And if you would follow the threshold of escape velocity, are you sure it's completely removed from the halo, or the return time is too large for you?
So I checked a bit, and some of it might indeed be reaccreted, but on a very long time scale, it needs to fall back. But I did measure some gas I mean, a small fraction of the outflows, but still some gas is permanently removed. Yeah, it reaches the escape velocity. Yeah, of course, the moment it reaches the edge of my box, I cannot follow it anymore. But yeah, we can consider for the disk or a reasonable time scale that it's lost. All right, if we look now at the periphery of the galaxy, so the region below 5 kiloparsec, let's say, we see that while the thermal pressure drops a lot, the cosmic ray pressure actually stays relatively high at this point. And this is because cosmic rays can propagate a bit everywhere throughout the disk, so they don't have this very strong cutoff the moment the star formation and supernova explosion rate drops with radius, and you will find cosmic rays a bit everywhere in the disk because they're able to very quickly propagate. And therefore what happens is that at the periphery of the galaxy, the cosmic ray pressure becomes dominant while the thermal pressure is completely negligible. And this is why at the periphery of the galaxy, you push colder gas into the halo. You will have only the cosmic ray pressure gradient as a mechanism to push gas out of the disk, so it will not push it as high, it will not accelerate it as much, but you will have colder gas because the thermal pressure is negligible. So I talked a lot, and I want to illustrate a little bit everything I just said. So the idea is that you have this galactic disk seen from the edge with a bunch of supernova explosions. The supernova heat up the disk, so you have a thermal pressure building up, which will be especially strong in the center of the galaxy where most stars form and most supernova explode, but it will decrease very quickly with radius. On top of this, you add this cosmic ray pressure gradient, which is a bit more uniform in the disk and will propagate more. I mean, the cosmic ray propagate more both in the disk and out of the disk. And if you combine those two mechanisms, you create a lot of outflows. So it will be especially strong in the center due to the combination of very high thermal pressure and the cosmic ray pressure gradient. And this is where you remove your hot, low angular momentum gas from the galaxy. And as you go more towards the periphery of the galaxy, you probably cannot read very well here. It says fountains and gas recycling. So you have those outflows that will stay closer to the disk and will be reactivated in fountain flows and recycled for future star formation. All right, so in the few minutes I have left, I would just like to introduce a bit the current work I'm doing. So one extension of this work is we have a new module in Univ, which is called CRESP, for Cosmic Ray Energy Spectrum, which allows to also model spectral components and spectral evolution of cosmic rays. This will not have any dynamical impact on the gas, but it will allow us to create synchrotron radio maps of our galaxy. I've shown some examples here. This allows, of course, direct comparisons to observations. Soon, we also have a PhD student working on introducing other spectral evolutions of other atoms, and this will also allow to create gamma ray maps for further comparisons. And what I'm currently doing is that I'm creating those synchrotron radio maps and try to see how they differ in very strongly outflowing galaxy, weakly outflowing galaxy. I'm trying to observe galactic fountains in the radio maps, etc. And so currently I'm working in Florence in Italy with Enrico Di Teodoro. And the idea is that I'm trying to see what happens in the Milky Way. So far I've talked a lot about Milky Way type galaxies. What happens in our own galaxy? Well, there's been some very puzzling observations lately from a recent paper from Enrico Di Teodoro that shows that in a nuclear outflow, so very close to the center of the galaxy, right above the center, about 1 to 2 kiloparsec distance, we found some gas clouds made of dense molecular cold gas. And this is a bit difficult to explain because you need very strong outflows to manage to push. So usually the gas that is pushed out of the disk is typically hot gas, or we found that with cosmic rays we have warm gas. But this dense molecular gas, it's a bit difficult to explain. So this is clearly in the outflows. This is gas that is going out of the disk, above the disk. On top of this, I already mentioned the Fermi bubbles in our own galaxy. So those are those very large structures extending far out of the disk, seen in X-ray and gamma ray maps. And that really show that, well, there's a presence of very strong outflows here. There's something that's creating those maps.
Do you know the proper motion of these gas clouds? Because maybe they're returning, not being just.
In the previous, in this one, they're outflowing. They have velocities of around 100 to 200 kilometers per second. That are really going out. Yeah. So this is a bit difficult to explain because our Milky Way doesn't have a very strong star formation rate in the center. It has some star formation, but it's not a starbursting galaxy. We also don't have AGN, so like active galactic nucleus. Our supermassive black hole Sagittarius A is fairly passive at the moment. So it's a bit difficult to really explain why we create such strong outflows. And the idea is maybe if we implement cosmic rays into the picture, maybe it will help us understanding at least part of those observations. So this is what I'm doing. I'm using Univ to run simulations of the Milky Way at high resolution. So here I'm close to 1 parsec to really try to resolve the Milky Way center. I'll just show you a very quick movie that shows my current work. So this is a very preliminary run, but here I form this ring here is the Centrum molecular zone, which is present in the Milky Way, which is forming a lot of stars. And this is the density on the left and the temperature on the right. And I'm trying to see how much outflows I'm able to produce this way. This is still without cosmic rays. And as we see, it's very difficult to form outflows higher than a few hundred parsec. While the observations from Enrico Di Teodoro are between 1 and 2 kiloparsec. So we really need to be able to push this cold clumps much higher. And now the question is, if I include cosmic rays in this, does the picture change? And this is what I'm working on currently.
But you don't have an answer yet.
No. This is really very preliminary. The simulation I just finished, not even finished, just got it from the last few days. So this is very in progress. I talked a lot, so I'll probably just leave you with my take-home messages, just a summary of everything I said. Thanks.
A few minutes left for questions or to Nicolas or Victor.
You use For your simulation, classical hydrodynamic equation. Just
And magneto-hydrodynamical.
explain me, you don't need any general relativity correction?
No. I mean, it's a simplification, but we have just standard MHD equations with just a term for the cosmic rays. But the cosmic rays only follow the transport equation, so we don't really have any relativistic. So we just assume that the cosmic rays propagate through advection and diffusion, and we don't really.
So it's completely Newtonian. Everything is.
You don't have a supermassive black hole inside the center of the galaxy either, right?
In my model, no, because I mean, I'm going to include it in the potential, in the gravitational potential, but it will have very little impact.
Any other questions?
Very simple one. Was in the very last movie you showed, the film.
Yes.
So what is the time scale? 1 second on the film is like 10 to how many years?
I slow down at some point. Yeah, so I evolved the simulation for almost 200 mega a year.
Mega years.
And you can see here the
Don't mind.
So yeah, I mean, it's still running, so we will write it.
All the questions, yes. So just a quick follow-up, maybe that will be
Yes.
useful for everyone, because I have a lot more questions we can follow up later. So you convinced me definitely the cosmic rays might be important for understanding.
Glad.
Well,
Great.
Relevant, yes, for understanding intergalactic dynamics.
Mhm.
Although I have one question for you. So in order to apply your equation, you need to have some kind of, gas has to be in casual contact and it has to be hydrostatic, I would say equilibrium, but actually, hydrodynamically coupled. But in principle, we know that gas can be very fragmented on small scales.
Yes.
You can also have turbulence.
Yes.
And then, of course, if this would be important, then in every cell, when you have advection and a flux, it would be the good representation of what is happening in the internal state of the gas. So do you have a feeling how much of this effect could be important to just, get this buoyancy or energy transport
I mean,
for your calculations?
So a very important parameter here is the resolution, right? So if you have a very low resolution, you will not represent those phases at all. And this is why we're really trying to push it to 1 parsec or even maybe below, because you can already start seeing a bit more how the gas is fragmented. And in the outputs, it will be very important. So what I've observed from making a few tests is that if you really want to look at the different phases and gas clouds and all, you need a very high resolution. But in terms of outflow rate, so the resolution has an impact on the star formation rate. So typically, if you increase your resolution, you will form more dense clumps, as you said, and this will tend to create higher density and therefore higher star formation rate. If you create higher star formation rates, you create more supernova explosions and therefore more outflows. So yeah, the question is, does it converge at some point if you push to higher and higher resolution? Kind of, we don't really know.
It's a close blending problem. The GR and to some extent, most of the cosmic simulations have the same problem, right? If the answer changes, if you change drastically
the
resolution, right?
Yes.
Okay.
Well, we're trying to reproduce, in the case with Milky Way, we're trying to reproduce typically the star formation rate of our own galaxy. So we try to reproduce the number of observables.
Can you actually estimate the pressure gradient somehow?
The cosmic rays?
Yeah.
Pressure gradient? This is very difficult to observe.
I can imagine.
Yeah.
But that would be nice statistics.
Yeah. So the only thing we could really compare is synchrotron radio maps or gamma ray maps. The cosmic ray themselves or the pressure gradient. This is very difficult to see in observations because it's difficult to translate.
So there's no smoking happen. Okay, thank you.
Sure.
And do we have any questions from Zoom?
No.
Can I just ask you, is Teoretycznej public? Do you have it
Yes.
publicly available?
Yes.
Okay.
So it's on GitHub. So it's very easy. So you just contact me or Michał Hanesh, and you can very easily get access to it. This is no problem at all. This is completely open.
Well, thank you, and let's thank Nicolas again.